Okay, so we're recording then. So yeah, we have a number of grad students. So as usual, everyone, you can speak up if you have a question, or if you want to chat it, that's fine too. I assume during the talk is good for you.
Yeah, whenever.
Okay.
I'd prefer during the talk just so that it tells me someone is there and listening.
Yeah. So I'm just gonna let you go ahead and introduce yourself and start from there.
Yeah. So I'm an assistant professor at Notre Dame. I did my PhD from UC San Diego. I am a chip designer. That's the kind of stuff I really enjoy. I guess I'll say I was kind of hipster because I got into neural networks and chip design before it was cool. That's what I joined grad school for. And then, a couple of years later, everyone jumped on the bandwagon. But I'll talk a little bit, a very teeny tiny bit about, how old some of these concepts are, how far away we are from being, what it's possible for us to be. And I can start whenever. I'll try and make this informal. So please feel free to interrupt me and ask questions. And I'll try and be as honest as I can. Some things, after the recording stopped, then we can talk about it more. Right, so I guess the topic that I'm going to speak about is going to be how do we design chips and accelerators for the next decade, let's say, right? Because it's starting to be that we want to use new materials, and it might not just be only silicon that we should be using if we want to extract maximum efficiency. So this is, a screenshot from the documentary that was about Lee Sedol and AlphaGo, and basically how DeepMind solved a problem a decade ahead of when we thought we would be able to solve it. This is about the same time that my lab got super into Go. So I'm pretty sure our advisor walked in on us playing Go rather than doing work, like for hours at end around the same time. Everyone got super hooked on this, right? This is our current view of what machine learning can be. It's completely superhuman, amazing, it does everything. In reality, though, this is what state-of-the-art machine learning is like if you deploy it in uncontained environments, right? Basically, random walk's gonna give you about the same result, does not perform the Roomba jousting as well as you'd hoped it would, and can be dangerous to all the people around if the knife stabs you in your foot rather than the balloon. So we know that biology actually, let me know if you're scared of insects, because this might be a bit of a nightmare after you find out. So this insect-like thing over here is a megapharma wasp. It's a parasitic wasp. It's smaller than many single-celled organisms, which means it could be around you anywhere. And it's about 200 microns by 200 microns by 200 microns in size. So about the width of a couple of human hairs, right? That's pretty tiny. This has 7,500 neurons, 3,000 of which are all dedicated to processing visual input. But this thing is way more capable in terms of complexity, in terms of capability, in terms of getting prey, avoiding predators, et cetera, over the course of its 1 week long lifespan. So look at the complexity of the system in the form factor, and then think back to those Roombas and realize that we actually do not have the capability to replicate the capabilities of this wasp, even now in an artificial system. So kind of what I try to do is a pie in the sky, how can we build one of these? Hopefully for benign purposes, but unfortunately, this thing can have many applications, as I'm pretty sure there's a Black Mirror episode on this or something similar. So, but I guess, my spiel is that I think if you want to build something that's at the edge of what's possible, right? Because if you think about this, is extremely energy efficient, capable of really complex tasks, and it can do all this in little to no, with little to no resources, kind of means we need to work across the stack, even though design abstractions are really useful to actually build these systems, build any complex system. But at some point in time, if you want to push the edge of what's possible, you're going to have to work across those abstractions and extract efficiencies. And the thing I normally talk about is, we need new ways of sensing signals, processing our sensory inputs. We need to rethink how we actually design the substrates which do all this processing, and we need to do algorithms in a way which actually benefits the hardware and isn't just done by people who have no idea how the underlying hardware is going to do the processing. In this talk, I'm probably going to skip the sensing parts of it and talk a little bit more on the computational side of things. So this is all well and good, but how does this actually match up with reality as we know it right now, right? We're not making microwasps tomorrow. So how does this match up? Well, domain-specific accelerators are getting more and more popular, and they're all implementing the same kind of machine learning algorithms in a way that might eventually, hopefully, lead to such kind of systems. Unfortunately, the algorithm hardware interaction that you see is really complex. So initially, I want to talk a little bit about the kind of interaction you can have and what all has an impact on that. Here are just a couple of examples. This is Vivens's Iris. This is Intel's Loihi. And this over here on the right is one of my chips. And we'll talk a little bit about what all has an impact where. So Mike Davies from Intel actually gave a talk on what is Loihi actually good at doing and what is it not good at doing. And partly what they said was, if you're going to use Loihi to implement standard DNNs, it's probably not going to be good at that, at least not as good as a DNN accelerator. So they talk about the kind of memory traffic patterns and the kind of, locality and everything that Loihi can exploit. And they say, we're actually going to be better at recurrent networks than we are in general at feed-forward networks, right? And this is not just limited to this specific accelerator. All these different types of accelerators I showed you earlier on, they're going to be good at different types of things. So as an example, Iris is not going to be the best at accelerating LSTMs, as an example, right? Loihi, they claim they are. And the analog accelerators I'll talk about are actually really good at doing certain kinds of things, say matrix vector multiplications, but not at graph processing, right? So there's all these different things that each one is useful for. And I think it bears a little bit of inspection to find out how should we even design our accelerators so that they might be better at the task we want them to do, so that eventually, if we want to make like the visual processing system for that microwasp, we can design an accelerator that might really, really be good at that, right? And fit in that form factor and use the attojoules of energy rather than, nanojoules of energy that you might traditionally do. So if you examine all these accelerators, the primary thing you end up noticing is that memory and memory fetches and just general reuse and all the complexities involved with data movement dominates whatever performance your accelerator gives you. So let's look at this chart on the left, but maybe in a little bit more abstracted view, right? So what we're saying is, you can get really, really good performance. So that's the upper horizontal line if you have really complex data flow and many parameters. If you have really complex data flow and fewer parameters, you can get really good performance, but maybe not as good as what you'd want in a data center. So this vertical purple area, hopefully it's visible, is what you would want in a mobile device. This horizontal area is what you'd want on your data centers. And this over here is, well, you've got really simple data flow, lots of reuse, but your performance is not good in either aspect. And so you're kind of limiting yourself. Now, taking a step back, what this means is we want to be able to run complex models, which are not just implementing matrix vector multiplications, and they'll have weird patterns of reuse and memory accesses and everything, which you can't just predict ahead of time. Now, taking one particular example of a spatial DNN accelerator, this is basically just a abstracted view of iris. Over here, if you just look at the amount of memory accesses you might need in order to implement a convolution, and consider the fact that SRAM accesses are going to be way, way, way more energy intensive than just doing a simple integer MAC, you'll realize that memory is indeed going to dominate pretty much everything that you do when it comes to AI/ML workloads, right? Now, this is a slightly different view of the same thing. What we did was we implemented an abstracted version of Iris. We used time loop, which is NVIDIA's tool for doing, extracting the best data flow, given a set of architectural constraints. And then we changed our memory technology. So we did ferroelectric devices, we did resistive RAMs, and then we did SRAMs. Now, mostly this is going to affect your density, right? And we extracted parameters from fabricated systems as well as purely predictive models with assurances from our devices colleagues that indeed we can achieve this if you just have a couple of devices, maybe not at the array level, but being optimistic, let's just go with something like this. And what you find is mostly, if you can make really dense and easy to read memory, your system performance is going to be amazing. And if you start building realistic memories like with SRAMs, that area is going to dominate, and the long bit lines and long word lines and all are what's going to end up being responsible for most of your energy expenditure, right? So this is not anything that's completely radical. This is actually, if you sit down and work through it, it's going to be clear that you're going to be dominated by memory accesses. And because those models, which have very few parameters in them, they have few parameters at the cost of reducing reuse. So each access gets amortized less and less. And so you do want to sort of reduce the impact of your memory in this case, right? And this is just one of those things which you have to come up with hopefully different ways of getting around. And so one way of getting around it is to, rather than have to ship your data, which is in memory, over to ALUs that are put at a different place with limited bandwidth and all, can we do something that will merge our memory and compute? So that ends up being the first, I'd say, thrust of what I'll talk about. Now, this is not a new idea. This is, for example, an analog, basically compute in memory neural network chip that Intel came out with sometime in 1989. So before you guys were born, for the most part, pretty close to when I was born. And it's supposed to be one of the most commercially successful analog neural network chips that were put out. They were doing compute in memory with flash, so non-volatile elements compute within, on the bit line, do analog accumulation, do neural networks, pretty much, what the modern, or the contemporary hype is all about. Even stuff from my own advisor's lab, they were doing embedded DRAM type devices with compute in memory, and they were getting something like femtojoule per multiply cumulate with adiabatic clocking and everything, right? So this is not completely new and radical. It's just that we now have different algorithms, different constraints, different architectural constraints, new materials. And so it bears looking at this kind of stuff again. So here, for example, is a proposal. This is out of Luca Benini's group from ETH on what a compute in memory CNN accelerator would be if you were to do this for ResNet 34. So ResNet 34 is one convolutional neural net. It's from the ResNet family. It has 34 layers. Now each thing or each blue square over here is basically a compute in memory system with some associate, I guess, added digital processing here. And we'll talk about the compute in memory system in a bit. So just think about it as a wide matrix vector multiplication system, right? Something like this would require 13 million elements all integrated onto a single chip. So hopefully, looking at this, you're going to come up with a few takeaways, right? Something like this tells us that the non-volatile memory elements are actually, hopefully, denser than using SRAM. So hopefully, those 13 million elements can fit in a smaller area, and we can have less energy spent on wires switching. B, we need many, many, many of them. 13 million elements is not super tiny. So it is going to still end up being a kind of large system. And just as an example of how one computer memory block might work, it ends up being quite intuitive, let's say, right? So imagine you had this magical memory that could store the value you want as analog values in resistance. Any voltage you apply in parallel along this horizontal line, so you should see the V1 to Vm applied horizontally as orange, would go through these resistances, and your output would basically be the current summation of each voltage weighted by the conductance, which just Kirchhoff's law or basic Ohm's law adds up and gives you these currents, where this vector of currents I1 through In becomes or encodes the output of a matrix vector multiplication if your vectors had been those voltages, and the matrix were encoded in this conductance, right? So, all right. I'm going to stop for a second here and ask if anyone has any questions on this, because I need to know. Otherwise, everything else is going to be even more boring. No? Okay. This is exactly like teaching.
We can wait a minute, see.
Yeah.
Anyone?
I have one general question.
Yeah.
Outside of research, has there been any product where they tried maybe in some sort of wherever they need accelerators, let's say high-end digital cameras or whatever, video cameras, where they have tried something along these lines?
Okay, good question. So E10 was actually a commercial product. So Intel sold these. B, there are a couple of startups right now. So, oh man, there used to be Isocline Mythic. Mythic AI is one, I guess, new one, which is, I guess, 3 years old, 4 years old. They're at the Series C or something right now. They've got some products on the market. They do flash though, right? So they're not doing RRAM or any of these newer, fancier, non-volatile memory elements. They're doing they're doing flash. DMAT, I think, is their name, or DMatrix, something like that. They do compute in memory as well. Yeah, that's the one. Yeah, they do compute in memory as well. And I think they're still pretty stealth. So I'm not sure precisely what they're doing. It's just known that they're doing compute in memory. And Marianne Verhest, I think she's out of IMEC. No, sorry, she's out of KU Leuven. And Luca Benini out of ETH have a startup. I don't remember the name. They are doing compute in memory. And of course, IBM. Right, so IBM's betting a lot on phase change based compute in memory systems. On the IBM side, I don't know if there's a product on the line, but I think they want to commercialize it. They've definitely been spending a lot of money on it, but yeah. Did that answer your question?
Yes, thank you very much. Thank you.
Actually, I'm Googling some of the history of this ETAN chip. It's kind of interesting, the articles in the early 90s, like claiming it might have the capability to be as intelligent as a cockroach and stuff like that. It's actually, I was trying to figure out if it's actually was in a product,
Can I ask one more question?
Yeah.
Because this thing will also very soon, the silicon real estate will start becoming a limiting factor if we start putting processing cores and memory. So one question is, so each, when we say in compute memory, so each, one question is how many cores does the state of the art have? What is the size or power equivalent of each core? Let's say A53 or A72 or whatever. How many of those cores? And secondly, so each one of them, there is no memory sharing. So each one works with its own dedicated memory. And during compile time, loading time, its own data has to be loaded there by a central control processor, which is more powerful. Is it something along those lines or different?
Yes. No, so it's basically that. Let's actually go back to the previous one. So this is basically saying each compute and memory core or unit is going to store all the parameters required for a single layer. In this case, you're spreading it out a little bit, but yeah, basically, all the parameters required are going to remain in that memory block. Now, given that modern non-volatile elements actually have a high write energy, that means you don't want to rewrite whatever you've stored there. It actually takes a lot of time and effort to rewrite even a single element there. So once you've written it in, you don't want to overwrite it with something else. So what you want is basically something that can store your entire set of parameters in this dense matrix form, so that all you're doing is matrix vector multiplication. And yeah, I mean, imagine you need 8-bit accurate values, right? So that becomes 13 million elements times 8 bits of memory spread out in this way, where each memory is, say, 576 times 576 in size. So it's not like you get a lot of array efficiency either, because these are kind of small and you have to spread them out everywhere. But the advantage in some ways is that you don't actually have to create multipliers and adders or too many multipliers and adders separately, right? You're actually doing a lot of analog compute that uses up the bit lines to simultaneously do addition on a cap there. So you don't need as many multipliers or adders either. So there is that trade-off you need to examine. That's honestly an open research question and something that my lab is looking at right now, because I basically told them, look, I did a lot of this during my PhD, but someone had better tell me whether it makes sense to do this more or not. So, prove me wrong. And I mean, it's open. There's no good answer to does it make sense to do this or not. I can definitely say if you can operate with really low bit precisions and you can make sure that all your neural network parameters fit in on-chip memory, then yes, that totally makes sense to do this. If not, then there are trade-offs that must be examined, probably on a case-by-case basis. Did I answer the question you asked, or did I just go off on a rant that was tangential to what you asked?
No, that was very helpful. Thank you very much. That actually raised one more very interesting question in my mind.
Okay.
Is the system architecture always like this, that there is a central processor and then there is a sea of small processing elements?
It doesn't need to be.
Is there any architecture in which there is more like a hierarchy? So each of these, what I'm trying to get at is, if we have a sea of, as it is shown, processing elements, it's necessary that they do not communicate among themselves much, because that will very quickly start becoming a bottleneck. They can only communicate with their adjacent processors, for that matter. which immediately brings to my mind that probably having a tree kind of a structure, control structure, where the central processor will delegate to its lower, it will delegate parts to its
right. Yeah. So there is a trade-off that you will see. Having this centralized thing can actually introduce more latencies than you might want, right? Remember, the way neural networks of this type don't normally work is you have some input activation and it hopefully just trickles across this network, right? And you basically have incidental computation happening at each processor. If you have some sort of a centralized system, well, that might end up being the bottleneck based on how large or how much data needs to propagate. Interestingly, my first paper in grad school was about using a fat tree-like routing architecture and having a centralized processor sort of take care of whatever routing across this. There are trade-offs just as with anything else. It might most likely be that your wire lengths are shorter with a nearest neighbor kind of thing, and nearest neighbors are most likely good enough. But again, it's an open question and not enough has been done in order to answer this. But actually, we're looking into NOC topologies and all that might be able to work well with this kind of traffic pattern. So I think we have enough people on the same page as me. So we can move on to the next part. Okay, so one thing which is not immediately apparent though, right, is that, oops, this, if you'll notice, is doing a forward matrix vector multiplication, right? But there are many ML models that require not just a forward matrix vector multiplication, but other types. So for example, you might want to do forward and then transposed, right? So X times W, where W is the weights and X is your input, and X times W transpose. You might need both, right? Or alternatively, maybe you want recurrence, like something. So those of you that are, no, I think we can just go this. So you might want to do X times W. The output feeds back. So, you know, X plus 1 or Xn plus 1 times W again, so on and so forth. This iterated, you know, matrix vector multiplier, what you'd use in iterative solvers, for example, right? You might need that kind of a data pattern. And this really nice structure, which we showed, which does just forward matrix vector multiplication, is actually not then that good at all these other patterns. So this is joint work we did over the last few years of my PhD, my postdoc, with, I think this was 4 universities and 5 years of pain, but we basically ended up developing this architecture, which can do in situ transpose for matrix vector multiplication so that you access not just the forward, but also the transpose, and you can do recurrence as well, all without moving data out of the core, right? So effectively, it ends up being a bunch of switches that you connect to your output driver, and based on whether you want to connect to the bit line or the source line, or in other words, if you want to connect to the data or its transpose, or the matrix or its transpose, you connect one of the 2 switches. And during runtime, you can reconfigure the switches, you know, so that you can dynamically change the data flow. Now, this is, I guess, the more, if you're mathematically inclined and you can visualize this, then this is one way of thinking about what the connectivity pattern is. A slightly different way of thinking about it is that you imagine all the red connections are one matrix, or they encode the forward matrix, right? And you arrange your data such that the green connections actually encode the transpose. Now, all you do is that you have a superposition of the red switches and the green switches connected to the same output sensing node. And you only activate one at a time based on whether you want the forward or the transpose. So I think this is a more intuitive way of thinking about it. It's just the superposition of 2 connections. Now, what this does is, as you'll notice, it trades off the density of my memory for a little bit of, I guess, flexibility in data flow, right? Now, this was a design we fabricated. And in fact, if you look at the layout, you'll notice our memory is reasonably dense over here, but we have these kind of long wires running over here, and we have our analog sensing over here in the corner. So what we've done is we've said, you know what, we might not need that much density of memory, but we do kind of want to be able to access the forward and the transpose, so we're going to make that trade-off. So one point which would not have been immediately clear from how I was evangelizing this whole thing, we don't even know how much memory density we want versus compute density we want. Right? So even that trade-off is still an open question. And what's a good balance to have for different networks or different types of networks? Here by networks, I mean neural network, so models, is still unknown and probably something that we do need a lot of people looking at. So we fabricated our chip. Now, many years of pain, got the chip back, and we decided to test it on what's called a restricted Boltzmann machine. So restricted Boltzmann machine kind of works like this. Imagine you've got your inputs and your outputs. It's a generative model. What it does is it kind of sloshes the inputs through the network over to the output. The output then gets told, oh, it dreams. So the output says the network classified this as a 2. So then propagate back all the way to the input what the network, well, I guess, models a 2 to be. And so it sloshes the data back and forth until it converges into an equilibrium of what the network expects. Now, with this model in mind, consider the kind of test we do, and that'll hopefully explain both the model and the chip itself. So you take a handwritten digit. So this is MNIST, and I think by now lots of people have been exposed to this. So you take a handwritten digit and you sort of block out part of the digit, right? So you obscure it and you say, okay, I'm going to give you partially filled in data. This network is supposed to finish out what it expects or thinks it is seeing. So you give it partial data, it goes to the model makes a prediction and says, oh, this looks kind of like a 2. I think a 2 should have pixels filled in at this point. So then it propagates the data all the way back, and all these things that are grayed out get filled in by the network. Right? So over to the left are examples of what we presented to the chip. Over to the right are what the chip thinks it is seeing. And I'm using things with quotes for those of you not looking at the screen, because we should not be anthropomorphizing these networks, but sometimes it's just easier to think about it like that. And so you do this back and forth, and you're able to reconstruct what was presented at the input. Now, over on the top right-hand corner, it's mostly just a quantifiable way of talking about the same thing. So if you had all your weights and all your operations performed at 64-bit floating point precision, you'd get a reconstruction error of 1.81. If you have, let's say, 3-bit equivalent weights or so, you'd get about 1.89, and that's about where we are at with 1.91. So we were between 7 levels and the next one. So we were way better than 9 levels, but a little worse than 7 levels. So we were 3-point-something effective bits of resolution stored within each RRAM element. Now, of course, this is one particular example. We also were able to use it for actual classification. So the standard MNIST classification thing. We showed how by doing voltage mode sensing rather than current mode sensing. So if you think back to what I'd spoken about with the output bit lines containing the sum of all the currents, if you implement a switched capacitor circuit that can actually accumulate the currents onto a cap and then feed that onto a comparator, you actually get the ability to average out your results over a bunch of reads. And that actually works much better than the current mode system, especially because you get to turn the entire array off because non-volatile elements. So you do one charge transfer, turn stuff off, do the sensing, and do the next charge transfer, turn stuff off, do the sensing. You can average over a couple of cycles and still get better energy efficiency for the same level of accuracy. And so we were able to do this kind of a setup, and we get pretty reasonable results for efficiency and accuracy on this network. Now, unfortunately, what I cannot do is show more recent results, but hopefully post-publication, that's when, Matt, invite me for the next one, please, and I will hopefully have much, much better results. But this is basically a summary of our energy efficiency. So if we're doing 1 bit input, 1 bit output, and internally analog computation, we're actually better than 2x better than other state-of-the-art. We are, especially given that we did all of our fabrication testing, etc., on a 130 nanometer design, and people are now looking at 40 nanometers. So this one here was out of TSMC, and higher this is, the better the value is. This is basically multiply qubits per normalized to power. Now, this is simply, so we published this at ISSCC, so the International Solid State Circuits Conference. And in order to get it published there, you basically need to have a table which slams everyone else's work and says you're the best. So that's kind of what's going on here. Our work is highlighted over here. And this is just other people's work, which they've done a really good job over here. We were able to, however, spend a little bit of, I'd say, effort in doing our sensing in a way that actually improves our efficiency quite a bit. Now, looking over here at the breakdown of energy, you'll notice that we're spending a lot of energy on our word line switching. This is basically a function of the memory device itself. We needed to have these high voltage transistors or high voltage tolerant transistors interfacing with those resistive RAM elements. And unfortunately, switching those uses up a lot of our energy. Our hope is if we can get access to a better technology, say 22 or 40, fingers crossed, then we should be able to bring down a lot of that energy, because it's a V squared energy expenditure on those word line switches. So bringing down the VDD should really help us. Okay, so I started off by saying we should rethink how we design computers. Now, of course, I'm biased. I do computer design, so it makes sense I'll start off with that. But on the code design side, you really do need to redo algorithms as well. Right? So it's not just about, oh, do a better job designing things. I've told you about what the good things are about RRAM as an example, but there's no free lunch. So there are definitely many things negative about RRAMs. One really simple thing is that you have a lot of variation. One thing which they don't tell you is that after you program a resistive RAM element, let's say to a certain value, and let's say I want the resistance to be precisely 23.5 kilo ohms. Over time, that resistance will actually change or drift over to the baseline. That's resistance drift over time, and we're showing what the impact of this resistance drift would be had we been doing compute in memory with such a system. So, given enough time, your resistance drift will cause your accuracy to drop down until you're basically just guessing. Right? This is just baseline chance, and then why even bother doing neural networks? Just toss a coin, you'll get the same answer. Device-to-device variation within RRAM arrays is also horrible, and same result. So if you have a lot of read variation, unless you calibrate or do certain a priori know where the error is coming from, you will see these kinds of massive drops in accuracy. Now, the way we have been doing RRAM programming has been to have this increasing level of pulses iteratively done until we can verify that our conductance is programmed to a certain value. So keep on doing tiny pulses until, and reading the output or reading the resistance until it's within a certain acceptable band, and then stop. And unfortunately, over time, it drifts away. So you do it again until it gets back into that range. And if you do it enough using that kind of a technique, then hopefully over time, you'll get this stable conductance value. So over here, we're showing for the chip I just spoken about, how the conductance drifts from its programmed conductance, target conductance value immediately after write versus a day after, right? So these are not as non-volatile as we had hoped they would be. Now, for the purpose of our previous chip, we were able to get this to work. We had some additional calibration things and all going on that helped us maintain network or model accuracy. But if you want to deploy this on a million IoT devices or something, that's not really likely, right? You can't go about calibrating all billion of them with this extremely expensive write verify process. It actually ends up being really expensive. So one thing I've been working on is encoded computing. And the key insight you should think about here is that there are ways of doing error correction such that...
Can I ask you a question about that last slide?
Yeah.
So when you do the measure after one day, is that after the same programming that you just did the measure immediately after write?
Yeah, so what we did was, so we took a chip, programmed in the resistance value, did the measurement, did this for a whole bunch of things. Like we had different elements, right? So we just programmed all the different elements and then let that chip be in the lab overnight, came in the next day, then just measured it, did not rewrite
Okay, so is that partly destructive read of the cell? Because when you apply a voltage to it, that changes the resistance, right?
It is unlikely to be destructive read because we had off-chip measurement for this particular thing. So we did really tiny pulses. Okay. So our write verify was actually not with on-chip components, it was with off-chip components. Okay. Yeah. But yeah, no, this is totally good, like perfect catch. So one way of, I guess, the traditional way of taking care of this is that you do ECC in your memory, right? But now I want to actually do computation in memory. So if I'm doing ECC, will I still be able to do the correct kind of computation? Turns out there are certain error correction techniques which are linear. Now, think back to linear algebra. When something is linear, it means that matrix vector product of that is still a valid linear transform. And so if I take my weight matrix and have a linear error correction code kind of transform applied to it, then any matrix vector product of this encoded matrix is still actually a valid code. And because I'm only performing these linear operations up until now, I can undo as long as I decode before applying any nonlinearity, I can recover accuracy. So this is one of those things which is not immediately obvious, but if you basically take it as, I'm just applying a bunch of linear transforms, it does not, everything that I've done is recoverable from those linear transforms. It ends up being quite a cool idea. So this is not my idea, that's why I can say it's cool. This was originally proposed by Pulkit Grover and Soumya Kaur from Carnegie Mellon. They were doing this for these nano, like single electron kind of FET transistors. They're information theorists, and so they're trying to say, well, is it even possible to do reliable computation with unreliable elements? we just did some additional design space exploration considering computed memory, but using similar ideas as them, right? Can you take linear error correction with unreliable memory, which can be prone to errors, such as this drift and all, and can you still get compute in memory sort of structures out of it? So yes, one simple question is, neural networks are inherently resilient. Why are you spending all this time with the overhead of ECC when just you can have a larger network and it'll probably be more resilient, right? So we did this first study of, okay, let's have our original network and just have, along the x-axis, some measure of variation. So just device-to-device variation. What would happen if we had the network now with 20% more features or 40% more features? So that's actually a pretty large increase in size. Turns out neither of those is as resilient as having ECC. And our ECC is in fact smaller than the 20% more feature map network. So it does make sense to do ECC in this embedded fashion, as long as you're able to do it with the precision you need. So I am going to just mostly allude to the kind of design space exploration that we did. So, we changed the array size. We looked at different amounts of, I guess, VDD reduction we could do while still, so kind of like a razor-like approach from Michigan, where once you have error tolerance, you can actually now increase the number of errors your system might see until you're actually capable of, until you're barely capable of correcting those errors, but you're still within the capacity of the ECC system, right? So that's generally the kind of approach we took. And turns out you can actually save a lot of energy by having ECC running just 2 or 3 iterations of decoding on this and just aggressively turning down the voltage so that, yeah, you might have more errors, but you can just correct for it because LDPC and some of these ECC techniques are just really, really good. Their capacity is higher than the amount of errors we would normally see. So yeah, I guess, just a short overview of what I've spoken about so far, right? So just with resistive memories, there are algorithmic problems that are still not resolved, right? We want to design algorithms that are more robust to device failure. Right now, it's all been from the hardware level, but we want more algorithmic work from that level as well. 2, I think this was one of you. You said, well, how would we move data around between these different cores, right? What's a good architectural solution there? This is super important and still open question. We've not even resolved this as yet. There are circuit techniques, right? I think we're just at the level of where we're exploring these new circuit techniques and seeing what different types of trade-offs we should have. At the moment, groups are mostly going for really dense memory arrays and just changing the periphery to have an ADC rather than a sense amp and saying, well, this is enough for it to be a reasonable computer memory system. But I think the space of trade-offs is much higher. And I mean, this is something I really want to explore, right? This is something that I've been looking at even in my own lab. So I guess I should ask, how much time do I have, Matt? 5-10 minutes?
Yeah, should probably wrap it up pretty soon. So
okay, so in that case, I think I'll just stop here. So what I spoke about was just with resistive memory, but there's actually a whole host of new devices coming up, right? And there are different problems that we'll face when we start integrating these. Variation is such a huge thing with these devices that I don't think we'll ever be rid of it, which means there's always going to be work to do at improving that, right? Getting better software or better algorithms that are tolerant to that variation, getting better tools that can give us, mitigate some of that automatically. There's an entire world of possibilities out there, right? And I think I should just want to thanking the sponsors, but more importantly, my students. They're the ones that did all the work. And my collaborators. So this is Philip Wong's group and Gert Kamberg's group. And yeah, I think just questions. Thank you.
All right. Does anyone else have any other questions?
Yeah, I have a question.
Yeah.
So in this slide where you were talking about the multiple bits per cell, you were going up to like, 7, 8, 9 bits. And obviously that's going to give good density and good power, but how did that affect your frequency?
We went to 3 bits.
Oh, sorry. There was a slide farther back that had like a bar graph. Maybe I misinterpreted it.
Bar graph. This one? Or this one?
Sorry, this one.
Okay. This was all with, oh, I see. There's not 7 bits, there's 7 levels. So 3 bits.
Oh, okay. That makes more
sense. Yeah. So, there might be papers that talk about 8 bits worth of effective storage in RRAMs. I have not seen any fabricated results. It's unlikely that entire arrays will give you that level of precision. Right? Getting 8 bits across an array where, remember, like these are weird oxide things, right? So dopants at one part of the device array versus the other will be totally different. So your read currents will be totally different and you need to be able to handle that dynamic range. And I just don't think it's possible to get 8 based on my understanding of current materials and like everything else.
Okay, yeah, that's why it shocked me. So thank you for clarifying.
Yeah. Sorry, I should have made that more clear. 7 levels. So little under 3 bits.
Cool. Any other questions?
Sure. Yeah. So great talk. I have another avenue for kind of curious to hear about both what you're doing inside your group and what you envision for the future, and that is with regards to tools, right? I mean, it's one thing to research new things, but what's the state of tools for how you do this for your group, and what would you envision for the future?
So, what I really want to do is set up something where we can have a full SoC environment, which can use computer memory, but maybe not have computer memory be the be all and end all, right? I've spoken to Matt about trying to automate the generation of these computer memory cores, and I do finally have a student who's working on that. So we're hoping to do enough clean hacking of OpenRAM that it is not basically like horrible glue on top of it. A lot of the stuff we've been working on right now has just been, getting the tech file to work well with TSMC65's DRC rules and everything, and kind of trying to make that also automated because we want to port that over to say 28 or 16, and even just like a lot of that stuff is where we're currently spending our time. The other thing I want to do is, and this is really aggressive and pie in the sky, but I really think this would be super cool, would be if we could use a lot of the RISC-V infrastructure to do the centralized controller be an actual processor on chip and not like 100 lines coming out of my chip, which I then control through an FPGA off chip, right? That would be super useful because right now, a lot of the problems you would see in real life are hidden because we just get all those 100 bits off chip and we have extreme parallelism, right? We don't worry about data staging or all of these things. We don't worry about cache coherency. But any real accelerator will have to at least think about addressing these problems. Yeah, I mean, ideally, I would love for like an actual proper, RISC-V system, open source the whole thing, give people enough that they can just press a button and replicate. I don't know enough about RISC-V myself. So that's one major limitation right here, right? I'm much more familiar with Verilog and those tools, not so much the chisel side of things, which I think it looks like RISC-V is going down that route, or does a lot of stuff along that route.
So you don't need chisel for RISC-V. That's definitely the case. You can do it with Verilog however you would like.
Okay.
So I guess with regards to your novel devices, can you build weaker forms of them with an older process? Maybe it doesn't have quite as exotic materials, for example, like this, Skywater process. Matt can tell you a lot more about.
So the cool thing is, all right, so whatever results I showed you were on 130.
Yeah.
Skywater is also 130.
But are any materials you need that are unique for your devices?
So actually, I can say that we're working on releasing the Skywater resistive RAM models right now to the public domain. So that's actually going to be open sourced soon.
Yeah.
Well, Jesse and I are actually working with them on that. So.
Okay.
Fantastic. Then in that case, even in Skywater, there is a they call it the Caravel, right? They have a harness that has a RISC-V core ready to go for you. So I think that would be great.
Yeah, no, so that's definitely one of the things I want to explore and try to get proper integration going.
Yeah.
Yeah.
Cool.
Yeah, the other thing, I guess I should. Sorry, I'm just gonna jump up over here to be able to talk about the sponsors. So I'm part of Jump Ascent. One of the things we're being funded for is actually trying to figure out, the computer memory is really good for dense matrix multiply, right? But a lot of these things have sparsity in them. So how do you trade off that sparsity versus density, right? One of the reasons I want a proper RISC-V kind of core in there is if we can have a RISC-V control data being offloaded either to computer memory or like a sparse accelerator, right? Or maybe even one of these systolic arrays, right? How would that trade off and what would be a good balance point? And I don't know, there's a lot of really interesting problems that you can start looking at once you've got that kind of infrastructure in place. But
definitely.
All right. Well, thanks for stopping by and giving an interesting talk.
Thank you.
Yeah, and I think I don't know, we had a small group today, but I think people may be having midterm hangovers or something. So we had midterms basically last week. So
yeah, no, I remember the quarter system is brutal. Actually, now that I'm on the I have one tomorrow. Which one?
Oh, a midterm. So
yeah. Which course?
We can do a review session.
CSE 121, embedded system design.
Okay, it's not horrible, I hope. Well, if it is, you're being recorded, so don't go on the record saying it's horrible.
Yeah.
But I'm happy you guys invited me. Looking forward to hopefully being there in person sometime.
Yeah, absolutely. Definitely stop by, and we'll chat more about some of the OpenRAM stuff, and also we have a lot of experience actually with the Caravel test harness too. So that could be an interesting thing to work together on. So
yeah, definitely. And yeah, Scott, if you've got any ideas for working on this, we can totally chat about this.
Definitely, especially the sparse stuff is catching my eye. Yeah, we can talk about that.
Yeah. Right. I'm gonna stop sharing.